Hey, what's up you guys? This is Ilarion Garbuzov with you, and today we'll have a talk on convolutional neural networks. Let's talk about it! Guys, I need your feedback, so push the like button, crash the like button and subscribe to my video channel on data science. In deep learning, a convolutional neural network, CNN or ConvNet, is a class of deep neural networks most commonly applied to analyzing visual imagery. They have applications in image and video recognition, recommended systems, image classification, medical image analysis, natural language processing, and financial time series. Convolutional networks were inspired by biological processes in that the connectivity pattern between neurons resembles the organization of animal visual cortex. Individual cortical neurons respond to stimuli only in restricted region of the visual field known as the receptive field. The receptive fields of different neurons partially overlap such that they cover the entire visual field. CNNs use relatively little preprocessing compared to other image classification algorithms. This means that the network learns the filters that in traditional algorithms were hand-engineered. This independence from prior knowledge and human effort in feature design is a major advantage. The name convolutional neural network indicates that the network employs a mathematical operation called convolution. Convolution is a specialized kind of linear operation. Convolutional networks are simple neural networks that use convolution in place of general matrix multiplication in at least one of their layers. A convolutional neural network consists of an input and output layer, as well as multiple hidden layers. The hidden layers of a CNN typically consist of a series of convolutional layers that convolve with a multiplication or other dot product. The activation function is commonly a ReLU layer and is subsequently followed by additional convolutions such as pooling layers, fully connected layers, and normalization layers, referred to as hidden layers because their inputs and outputs are masked by the activation function and final convolution. Mathematically, it's technically a sliding dot product or cross correlation. This has significance for the indices in the matrix in that it affects how weight is determined at a specific index point. When programming a CNN, the input is a tensor with shape number of images by image height, by image width, and by image depth. Then, after passing through a convolution layer, the image becomes abstracted to a feature map with shape number of images by feature map height, by feature map width, by feature map channels. A convolutional layer within a neural network should have the following attributes: convolutional kernels defined by width and height, the number of input channels and output channels. The depth of the convolutional filter, the input channels, must be equal to the number channels, depth, of the input feature. Convolutional layers convolve the input and pass its result to the next layer. This is similar to the response of a neuron in the visual cortex to a specific stimulus. Each convolutional neuron processes data only for its receptive field, although fully connected feed-forward neural networks can be used to learn features as well as classify data. It is not practical to apply this architecture to images. A very high number of neurons would be necessary even in a shallow opposite of deep architecture, due to the very large input sizes associated with images, where each pixel is a relevant variable. For instance, a fully connected layer for a small image of size 100 by 100 has 10,000 weights for each neuron in the second layer. The convolution operation brings a solution to this problem, as it reduces the number of free parameters, allowing the network to be deeper, with fewer parameters. For instance, regardless of image size, tiling regions of size 5 by 5, each with the same shared weights, requires only 25 learnable parameters. By using regularized weights over fewer parameters, the vanishing gradient and exploding gradient problems seen during backpropagation in traditional neural networks are avoided. Convolutional networks may include local or global pooling layers to streamline the underlying computation. Pooling layers reduce the dimensions of the data by combining the outputs of neuron clusters at one layer into a single neuron in the next layer. Local pooling combines small clusters, typically 2 by 2. Global pooling acts on all the neurons of the convolutional layer. In addition, pooling may compute a max or an average. Max pooling uses the maximum value from each of a cluster of neurons at the prior layer. Average pooling uses the average value from each of a cluster of neurons at the prior layer. Fully connected layers connect every neuron in one layer to every neuron in another layer. It is in principle the same as the traditional multi-layer perceptron neural network. The flattened matrix goes through a fully connected layer to classify the images. Each neuron in a neural network computes an output value by applying a specific function to the input values coming from the receptive field in the previous layer. The function that is applied to the input values is determined by a vector of weights and bias, typically real numbers. Learning in a neural network progresses by making iterative adjustments to these biases and weights. The vector of weights and the bias are called filters and represent particular features of the input. A distinguishing feature of CNNs is that many neurons can share the same filter. This reduces memory footprint because a single bias and a single vector of weights are used across all receptive fields sharing that filter, as opposed to each receptive field having its own bias and vector weighting. A CNN architecture is formed by a stack of distinct layers that transform the input volume into an output volume through a differentiable function. A few distinct types of layers are commonly used. The convolutional layer is the core building block of a CNN. The layer's parameters consist of a set of learnable filters or kernels, which have a small receptive field but extend though the full depth of the input volume. During the forward pass, each filter is convolved across the width and a height of the input volume, computing the dot product between the entries of the filter and the input and producing a two-dimensional activation map of that filter. As a result, the network learns filters that activate when it detects some specific type of feature at some special position in the input. Stacking the activation maps for all filters along the depth dimension form the full output volume of the convolutional layer. Every entry in the output volume can thus also be interpreted as an output of a neuron that looks at a small region in the input and shares parameters with neurons in the same activation map. Three hyperparameters control the size of the output volume of the convolutional layer: the depth, stride, and zero padding. The depth of the output volume controls the number of neurons in a layer that connect to the same region of the input volume. These neurons learn to activate for different features in the input. For example, if the first convolutional layer takes the raw image as input, then different neurons along the depth dimension may activate in the presence of various oriented edges or blobs of color. Stride controls how depth columns around the special dimensions, width and height, are allocated. When the stride is 1, then we move the filters 1 pixel at a time. This leads to heavily overlapping receptive fields between the columns and also to large output volumes. When the stride is 2, then the filters jump 2 pixels at a time as they slide around. Similarly, for any integer s, a stride of s causes the filter to be translated by s units at a time per output. Sometimes it is convenient to pad the input with zeros on the border of the input volume. The size of this padding is the third hyperparameter. Padding provides control of the output volume special size. In particular, sometimes it is desirable to exactly preserve the special size of the input volume. Another important concept of CNNs is pooling, which is a form of nonlinear downsampling. There are several nonlinear functions to implement pooling, among which max pooling is the most common. It partitions the input image into a set of non-overlapping rectangles and for each such subregion outputs the maximum. Intuitively, the exact location of a feature is less important than its raw location relative to other features. This is the idea behind the use of pooling in convolutional neural networks. The pooling layer serves to progressively reduce the spatial size of the representation, to reduce the number of parameters, memory footprint, and amount of computation in the network, and hence to also control overfitting. It is common to periodically insert a pooling layer between successive convolutional layers, each one typically followed by a ReLU layer. In a CNN architecture, the most common form is a pooling layer with filters of size 2 by 2 applied with a stride of 2, downsampled at every depth slice in the input by 2 along both width and height, discarding 75% of the activations. ReLU is the abbreviation of rectified linear unit, which applies the non-saturating activation function. It effectively removes negative values from an activation map by setting them to 0. It increases the nonlinear properties of the decision function and of the overall network without affecting the receptive fields of the convolutional layer. ReLU is often preferred to other functions because it trains the neural network several times faster without a significant penalty to generalization accuracy. Finally, after several convolutional and max pooling layers, the high-level reasoning in the neural network is done via fully connected layers. Neurons in a fully connected layer have connections to all activations in the previous layer, as seen in regular, non-convolutional, artificial neural networks. Their activations can thus be computed as an affine transformation with matrix multiplication followed by a bias offset vector addition of a learned or fixed bias term. The loss layer specifies how training penalizes the deviation between the predicted output and true labels and is normally the final layer of a neural network. Various loss functions appropriate for different tasks may be used. Softmax loss is used for predicting a single class of k mutually exclusive classes. Sigmoid cross entropy loss is used for predicting k independent probability values. CNNs use more hyperparameters than a standard multi-layer perceptron, while the usual rules for learning rates and regularization constants still apply. The following should be kept in mind when optimizing. Number of filters. Since feature map size decreases with depth, layers near the input layer will tend to have fewer filters, while higher layers can have more. To equalize computation at each layer, the product of feature values with pixel position is kept roughly constant across layers. Preserving more information about the input would require keeping the total number of activations, number of feature maps times number of pixel positions, none decreasing from one layer to the next. Common filter shapes found in the literature vary greatly and are usually chosen based on the dataset. The challenge is thus to find the right level of granularity so as to create abstractions at the proper scale given a particular dataset and without overfitting. Max pooling shape. Typical values are 2x2. Very large input volumes may warrant 4x4 pooling in the lower layers. However, choosing larger shapes will dramatically reduce the dimension of the signal and may result in excess information loss. Often non-overlapping pooling windows perform best. Regularization is a process of introducing additional information to solve an ill-posed problem or to prevent overfitting. CNNs use various types of regularization. Because a fully connected layer occupies most of the parameters, it is prone to overfitting. One method to reduce overfitting is dropout. At each training stage, individual nodes are either dropped out of the next with probability 1 minus p or kept with probability p, so that a reduced network is left. Incoming and outgoing edges to a dropped-out node are also removed. Only the reduced network is trained on the data in that stage. The removed nodes are then reinserted into the network with their original weights. Since the degree of model overfitting is determined by both its power and the amount of training it receives, providing a convolutional network with more training examples can reduce overfitting. One of the simplest methods to prevent overfitting of a network is to simply stop the training before overfitting has had a chance to occur. It comes with a disadvantage that the learning process is halted. Another simple way to prevent overfitting is to limit the number of parameters, typically by limiting the number of hidden units in each layer or limiting network depth. A simple form of added regularizer is weight decay, which simply adds an additional error proportional to the sum of weights L1 norm or squared magnitude L2 norm or the weight vector to the error at each node. For many applications, the training data is less available. Convolutional neural networks usually require a large amount of training data in order to avoid overfitting. A common technique is to train the network on a large data set from a related domain. Once the network parameters have converged, an additional training step is performed, using the in-domain data to fine-tune the network weights. This allows convolutional networks to be successfully applied to problems with small training sets. Now, as we listen to the theoretical part, let's see it in Python. There are a few general steps when creating a neural network which should be the basis for any problem. These steps are fundamental to understanding how CNNs work and the different problems at hand which require tweaking of the CNN. First of all, identifying the problem. What we want to get out of this code is to be able to feed any picture to our model, and through convolutional neural networks it should classify what type of item it is. We need to import necessary libraries. TensorFlow is a free open source platform for creating algorithms in machine learning. TensorFlow really aids in the building of convolutional neural networks to solve complex tasks efficiently. NumPy is a library which includes concepts from linear algebra, such as arrays and matrices, which will make sense later on. Keras is a great API provided by TensorFlow and is one of the leading high-level neural networks APIs. It is written in Python and supports multiple backend neural network computation engines. We need to acquire the data. The data was provided in the MNIST dataset, which can be accessed by the Keras API in TensorFlow. Fashion MNIST is a dataset of Zalando's article images, consisting of a training set of 60,000 examples and a test set of 10,000 examples. Each example is a 28 by 28 grayscale image associated with a label from 10 classes. Zalando intends Fashion MNIST to serve as a direct drop-in replacement for the original MNIST dataset for benchmarking machine learning algorithms. It shares the same image size and structure of training and testing splits. Each image in our data is 28 pixels high and 28 pixels width, for a total of 784 pixels in total. Each pixel has a single pixel value associated with it, indicating the lightness or darkness of that pixel. With a higher number, meaning darker, this pixel value is an integer between 0 and 255. The training and test data sets have 785 columns. The first column consists of the class labels and represents the article of clothing. The rest of the columns contain the pixel values of the associated image. Importing our NumPy library would help us tremendously while working with these 28 by 28 arrays. So we've got labels of our different items from 0 to 9, and it starts from t-shirt to at 0 to ankle boot at 9. The Fashion MNIST is available directly in the Keras datasets API, so you can load it like this. Just tf.keras datasets.fashion MNIST and then MNIST.load data. The next thing we'll want to do is split our data into training and test data, so we can train our model with given labels and then give our model test data, which the model can apply through learning from the training data onto the test data. Here we're dividing it to training images and training labels, test images and test labels, and importing matplotlib for plotting our dataset. An interesting thing when working with images and data is visualizing it. So we'll import the matplotlib library, which can help us plot our data into images that are visually appealing. For example, our first object, which is at index 0, is a boot. So here we input a matplotlib and plot the 28 by 28 image that is a boot. We can see that our 28 by 28 pixels are depending on the item. Every pixel has its own value from 0 to 255. Sorry. So after that we need to normalize the data dimensions so that they are of approximately the same scale. So we normalized training images and test images. We need to reshape input data from 28 by 28 to 28 by 28 by 1 for the convolutional layer. Here we're reshaping it, and now we can create our model. So we define our model with a few keywords. Sequential defines a sequence of layers in the neural network. We must define the input shape in the first layer of the neural network. So at the first layer we would use convolutional 2D with 64 filters, kernel size 2, the same pairing, and the activation is ReLU, and the input shape is 28 by 28 by 1. And ReLU effectively means if x more than 0, return x, else return 0. So what it does
is it only passes value 0 or greater to the next layer in the network. After that, we would use max pooling 2D with the pool size equals 2 and the dropout with 0.3 coefficient. So after that, we are using the same convolutional 2D with 32 filters, kernel size 2, and padding, the same padding, ReLU activation, max pooling with the pool size 2 and dropout. After that, we are using the flatten, and that means we are converting our 2D array of pixels into a 1D list of each pixel. And dense layer with 256 neurons and activation ReLU is the keyword which we use when adding layers to a neural network. In our case, after convolutions, we are using dense layer, and then the dropout, and after that we are using softmax with 10 classes. So it takes a set of values and effectively pick the biggest one. So for example, if the output of the last layer is the vector of 10 values, it saves you from fishing through it looking for the biggest value and returns it into your label. The goal is to save a lot of coding. So take a look at the model summary. We've got convolution, max pooling, dropout, convolution, max pooling, dropout, flatten, dense, dropout, dense, and the total parameters for such a shallow network is 400,000, and all parameters are trainable. So here is the summary. And after that, we need to compile our model. So the compile means that it's actually building our model. We do this by compiling our model, and there are two very important parameters we need to have filled out: optimizer and loss function. The loss function measures how much error we made between the actual value and what the model gave us. Then using the error value from the loss function, the optimizer function creates a better guess on the next try. The matrix parameter will basically tell us our accuracy of our estimate on each guess. So we're compiling and train the network, and we see feeding, and after the compiling we are feeding our network with train images and train labels, and on 5 epochs. Now we've created our model, but how will we give it the data to train on? We do this by feeding our model on our training images and training labels. We feed the model with to have it figure out the relationship between the training data and its actual labels. So in the future, if you have data that looks like the training data, then it can make a prediction for what data would look like. The number of tries we want to run the model is called epochs, and there is a thing as too much overfitting, so there is a certain amount that is ideal. And we train it on 5 epochs. After we train our model, we see the final loss and accuracy. So on 5 epochs we see that we've got good accuracy rate. When we train our model, we want it to work on data that doesn't give it the final answer, and that is called our test data. It returns a list with the loss of our model and the accuracy. In our case, our model has an accuracy of 90% and the loss of 26, even better than on the train data. So this is a good result for such a little such a shallow network and such a little data set. And after that we can predict the labels on test data and see the labels. And let's quickly repeat all the stuff. So first of all, we need to import the libraries, load the data, explore the data, normalize the data, reshape input data for convolution neural network, create a model, compile a model, feed the model with a trained data set, see the loss and accuracy on training data set, evaluate it on the test data set, and after that we can predict the result. And when we was creating a model, we were using convolutional neural networks with max pooling and dropout, as I told you at the first part of our talk.
Thank you. See you tomorrow.